frequencies, and current. At the end of this module, you will be able to describe the differences between low and high frequencies, understand how different frequencies can make a difference, explain how to recognize when a different frequency should be used, and describe how frequencies are directly related to current. When discussing frequencies, it's important to remember that we're discussing what occurs within the span of 1 second in time. Units are vital, as adding a k to the number is adding 1,000 to the number. 1 Hertz equals 1 cycle per second. 1 kilohertz equals 1,000 cycles per second, or 1,000 hertz. As current flows away from the transmitter, the current flow is positive. This is when the magnetic field is being built. As current flows back towards the transmitter, this is negative current flow. The magnetic field collapses. In this example, the top sine wave symbol represents a low frequency. The bottom sine wave symbol represents a high frequency. If you were to stretch each one of those lines out, and they represented a bookshelf, which bookshelf could hold the most amount of books? The low frequency or the high frequency? The high frequency. In this example, we're not talking about books on a bookshelf, we're talking about current flowing on our line in a snapshot of 1 second in time. The higher the frequency, the more current is present in 1 second. That's sort of an abstract way to think about it. Surface area. Another analogy is something I call the flash analogy. If I were to go to the grocery store and load groceries into the kitchen from my vehicle back to my vehicle, and I was really fast, I might be able to do that in 1 second. My frequency would be 1 hertz. The payoff in this example would be 2 bags of groceries in the kitchen. If the flash stopped by, he's a lot faster than me. Let's say he's able to go from my vehicle to the kitchen and back to the vehicle 1,000 times every second. In this example, the flash's frequency would be 1 kilohertz. Who's putting more groceries in the kitchen? Me or the flash? Well, it's the flash. Why? Simply because he's much faster than I am. He's able to put more groceries in the kitchen in 1 second than me. Instead of groceries in the kitchen, we're talking about how much current is present on the target conductor in 1 second in time. The higher frequency is putting more current on the line in 1 second than a lower frequency. This is why different frequencies sometimes can and will do different things. Frequencies used for electromagnetic pipe and cable locating, they range from about 1 Hz to 480 kHz. There are no frequencies for conventional locators as low as 1 Hz. There are some that get down to around 3 Hz. From 1 Hz to 20 kHz, that is known as the audio band for lower frequencies. From 20 kHz to 480 kHz, that is the higher frequencies in the radio band. We say, in general, low frequencies tend to go the distance, high frequencies tend to fight resistance. If we were to cut up the audio band and the radio band 2 more times, we would end up with 4 different categories. From 1 Hz to 10 Hz, that is called the low-low band. From 10 Hz to 20 kHz, the low-high band. From 20 kHz to 200 kHz, high-low. And from 200 kHz to 480 kHz, high-high. Each frequency band category has potential to offer a variety of different utility locating frequencies. Different frequencies sometimes can and will do different things. The rule of thumb is, try something. If that doesn't work, try something else. It's important to remember that there is no such thing as the best frequency. The best frequency is the one that works. Common frequencies generally range from 60 Hz passive, 128 Hz, 256 Hz, 512 Hz, 8.19 kHz, 9.82 kHz, passive radio band, which is generally around about 28 kHz, 33 kHz, 65 kHz, 83 kHz, 200 kHz, and then there is no locate frequency between 200 and 480 kHz, 480 kHz being the highest frequency that you could use. This is because the AM radio band begins at 530 kHz. The interesting thing about 480 kHz is that it has the potential to jump a broken tracer wire and continue the locate, and push past an insulator if one is present on the line and continue the locate. In this example, there is no far-end ground on the dummy neutral scenario setup, nor is there a ground on the transmitter. The scenario does not contain a ground in the circuit whatsoever. The reason for that is to showcase how different frequencies can fight resistance better than other frequencies independent of all other factors. On the transmitter, 512 Hz is outputting 0 milliamps. When the frequency is increased to 33 kHz or 33,000 Hz, the current output increases to 2 milliamps. With the highest frequency this transmitter can broadcast, 200 kHz, the milliamp output is 10 milliamps. As the frequency increases, so does current. The higher frequencies are better at fighting resistance than the lower frequencies. There are 3 ways to assess current flowing on a utility line using your peak signal indication: good, okay, and poor current. Good current is defined as being a good, strong, and steady peak response. The peak number, digital bar graph or analog needle display, and the audible tone all lock in steady and do not fluctuate. This receiver indication shows good current flowing on a line and can be used to mark facility location. OK current is defined as being a slightly fluctuating peak response. The peak numbers, digital graph or analog needle, fluctuate only slightly. This is an example of OK current and can be used to mark facility location only if a good current indication cannot be achieved by troubleshooting at the transmitter. Poor current is defined as a wildly fluctuating peak response. If this is the first thing seen on the receiver, verify the receiver and transmitter are set to the same frequency. Sometimes an incorrect frequency setting can appear as a poor current reading if a button has been pressed by mistake. If you see a poor current reading or end up at the incorrect utility type at point B, a change in the transmitter must occur. It is never okay to mark utility location with a poor current reading. A change of the transmitter must be conducted to try and make a poor current reading either an OK or a good current reading. As locators, it is vital to know the difference between good information and bad information, and to know to never mark bad information. It is okay to mark good current or OK current, but it's never okay to mark poor current. You should now be able to describe the difference between low and high frequencies, understand how different frequencies can make a difference, explain how to recognize when a different frequency should be used, and describe how frequencies are directly related to current.